In today's lecture, we will be discussing about fundamental properties of powder particles and their characterization. In this video, we will be discussing about the methods to measure particle volume and particle surface area. This video explains about how particle volume and particle surface area can be measured. Now, let's get into the details. The fundamental properties of particles include particle size and distribution, particle number, particle surface area, particle shape, and particle volume. In this lecture, we will be discussing about particle surface area and particle volume measurement. Now let's see particle volume. How particle volume can be measured. Now, for this particle volume measurement, we will be making use of Coulter counter instrument. Hence, this method is also known as Coulter counter method, as the instrument used in this is Coulter counter. This method is also known as Coulter counter method. Now, let us discuss about the principle behind this Coulter counter. Now, our aim is to determine the particle volume, how much volume will be occupied by the given powder sample. Now, we should make sure that we need to make a suspension of the given powder sample. Now, let us see how this actually works. Before that, let's discuss about the construction of this equipment, the Coulter counter. This Coulter counter will be having two electrodes. So one electrode is dipped into a beaker. This beaker, one is dipped in this beaker. Now this beaker will be having our sample, which is made as a suspension with the help of electrolyte. Normally, we'll be making use of 0.9% sodium chloride solution, nothing but the saline. We should make sure that this electrolyte should not flocculate our powder sample. So the powder sample and the solution we need to choose in such a way that it produces deflocculated suspension. The other electrode of this instrument is dipped into an electrolyte solution which is placed in a glass tube. So here we will be able to see one electrode and the second electrode. Second electrode is placed inside the glass tube. Now this glass tube will be filled with the electrolyte solution. This is a setup. Now at the bottom of this glass tube we'll be having small pore or orifice. Now This whole glass tube is connected to vacuum. It is set up in such a way that the particulate solution from the beaker, means our sample solution from the beaker, will be entering through this orifice. All the particles will be sucked through this orifice into the glass tube. Now this is the basic construction. Now this whole setup, now this all these electrodes will be connected to an amplifier, will be connected to a, a monitor which shows the voltage differences, and that is connected to a monitor where the pulse changes will be read. Now this is the whole setup. Now let's see how this equipment is used to determine the particle characteristics. Let's see how it works. Now this is the working diagram of Coulter counter, where we are seeing the two electrodes, one electrode and the second electrode. So this second electrode is placed in a glass tube. Now at the bottom of the glass tube we will be able to see an orifice, which is magnified here, an orifice. Right, these electrodes are connected to a pulse amplifier. Now let us discuss about how this actually works. Now the powder sample is to be taken, and then the given powder sample, for which we need to determine the surface, the volume, we need to take it and we need to add electrolyte solution to get a dilute suspension. Now this suspension is taken in this beaker. Is taken in this beaker. And a known volume of suspension is pumped through the orifice, so that only one particle will be entering into the orifice at a time. Now, here the electrodes are connected to the pulse amplifier, and these are to be set up in such a way that when a constant volume of electrolyte is passed, when constant amount of electrolyte is passed through this orifice, there will be some change in the voltages, because in this glass tube we are having electrolyte solution, and in this beaker also we are having electrolyte solution in which our powder sample is dispersed. So if there is some traveling of particle occurs across this barrier, there will be some displacement of electrolyte solution. Because of this displacement of electrolyte solution from the glass tube, when a particle enters, definitely there will be some change in the voltage across the electrodes. Let me explain this once again. Our aim is to determine the particle volume. Now here this consists of the electrodes One electrode is placed in a sample suspension which is made with electrolyte solution. The other electrode is placed in a glass tube having the electrolyte solution. Now, in case if our sample as individual particle is sent through the orifice, this particle will displace electrolyte solution from the tube. So there will be some deflection in the voltage because of this displacement of the electrolyte, which is read as some resistance changes between the electrodes. Now the change in this amplifier, the change in this voltage or the electrical resistance is proportional to the volume of the particle. Now this is again converted into the voltage and then it is amplified electronically. So and then we'll be getting the final output. Now based on the impulses generated, we can know the volume of particle. So here we will be having two threshold values of the analyzer. Now this is completely related to the instrument. Now here by varying this threshold values, we can count the number of particles in a constant sample size, and thus the particle size distribution can be obtained. The particle volume can be obtained. How many particles are being passed through the orifice? Now suppose if there are n number of pulsations or the voltage changes are seen, which indicates n number of particles passing through the orifice. The amount of voltage created represents the change, the respective change in the pulsations represents the volume of the particle. Because here, for the particles which are producing pulses, we will be setting up two threshold values for the analyzer. So if a particle produces pulsation between these values, we'll be sharing the same particle volume. That is how we can determine the particle volume, particle size, number of particles, particle size distribution can be determined. Now especially this method is used to study the dissolution characteristics. Now how much amount of drug is being dissolved, and also we can determine the particle growth also, because in some formulations crystal growth will be seen on long standing. So to study the crystal growth or particle growth, and also to study the inhibition of bacteria by antimicrobial agents can be studied. So this is an instrument that can be used according to its purpose, where the working principle remains the same. So from this is the working diagram, where we will be seeing one electrode and the second electrode in the glass tube. So on the second electrode we are having some orifice. When a particle passes through this orifice, there will be some change in the there will be some deflection here, change in the voltage, because when a particle enters, it is displacing the electrolyte solution here. So there will be some change as when electrolyte moves, or there will be some current generated between the electrodes that can be easily read here. So if there are n number of changes in the voltage, it represents n number of particles passed through this orifice. And the amount of pulsations based upon the threshold values, we will be able to determine the particle volume. That is how we will be making use of Coulter counter to determine the particle volume. These are the advantages and disadvantages of Coulter counter. The disadvantages of this method is we need some electrolyte to make a suspension of the powder sample, and we need to choose carefully this electrolyte solution in such a way that it should produce a deflocculated suspension, not a flocculated one, because aggregation of particles can give false results. Now, the most advantageous thing about this method is this instrument is used or can be operated in a size range of 0.5 to 1000 micrometers, and a large number of particles can be counted in lesser time because each single count will takes less than 30 seconds. So within a less time we can be able to count a large number of particles. So the most advantageous thing of this is we can determine the number of particles, the particle size, and also the particle volume. This is about the particle volume measurement. For particle volume measurement, we will be making use of Coulter counter instrument. Now, we will discuss about particle surface area. Now, how can we determine this particle surface area? That we will be discussing now. Now, in this particle surface measurement, we will be considering two methods. The first one is adsorption method, and the second one is air permeability method. Now let's look into the adsorption method. Now again, in this adsorption method, we will be making use of two working principles. The first one is by using solute that forms monolayer, and then the second principle is by using gas adsorption on powder sample. Now let's discuss one by one. Now first of all, we will be discussing about adsorption method, how this adsorption method can be applied in measuring particle surface area. And in that, we are having two principles. The first one is by using solute that forms monolayer, and by adsorption of gas onto the powder. Now let's get into this method. The first one is adsorption method. The name itself indicates here the adsorption phenomena plays a major role. What is meant by an adsorption phenomena? Adsorption phenomena is the process in which a surface of two particles get adhered. There will be some physical sorption process that takes place between two surfaces. Generally, the particles of a very fine size, means the particles having a greater surface area, are known as good adsorbents. Now we are considering this point as our working principle. Now the powder sample is taken. The powder sample to which we need to evaluate the surface area is taken. Now to this powder sample, we will be adding gas or solute to form a monolayer. Now let's see diagrammatically. Let's consider this as the powder sample. Now this as the powder sample. A packed powder sample. Now this packed powder sample, if you see inside, though each powder particle will be present like this, the closely arranged particles. Now suppose if another solute or another gas is passed through this plug of powder, what is the fate of this powder? The gas, while passing through this powder, will get adsorbed onto the powder particles, right? The amount of gas entering and the amount of gas exiting will be different because of some of the gas molecules get adsorbed. Now we will be considering this principle to determine the surface area. So more the surface area, more will be the adsorption. So if the surface area is more gas will be adsorbed and less gas will be exited. So this is the basic principle, and this principle will be varied based upon the instrument which we use. Now let's discuss one by one. Now let's consider this method by using a solute which forms a monolayer. The name itself indicates here in this method we'll be making use of a solute. So adsorption of a solute from its solution onto the surface of the powder whose area is to be determined would be our working principle. Now let's see in detail how this is applied. Now we will be having a sample let's discuss a first method by using solute that forms monolayer. Now in this method we need to have solute plus medium plus powder sample of which we need to calculate the surface area. We need to select the medium in such a way that the solute and the powder sample will remain insoluble. All these things should be insoluble. Now let's discuss. A known amount of powder is then added to the solution. Now let's discuss this. Take a beaker, add some medium, add your solute, some solute, and some solute is to be chosen in such a way that these should be insoluble. And to this we are having solute plus medium, and to this we need to add in our sample to which we need to determine the surface area. Now we need to add a known amount, say for example take 10 grams. Okay, a known amount of sample is taken and then it is added to the solution. So we are having our sample is added and these are stirred properly. Now during the stirring, this solute molecule and this powder sample gets adsorbed with each other. Adsorption forces will be absorbed. No, all will be absorbed. So we are having many particles, all will be adsorbed. So after equilibrium has attained, means after mixing, now this solution is filtered. This is filtered. So when this is filtered, when this is filtered, now on this filter, we will be having the insoluble solute which is adsorbed to the powder sample will be actually filtered out. So all the particles will be filtered out like this, which have been adsorbed, and this solution here will be having the medium along with the powder sample. So now this is checked for the amount of particles present. Now there will be some difference in the quantity that is added in the beginning and that is found after filtration, right? Now if we have added 10 grams of the sample into the beaker and after stirring, some of the particles will get added to the solute particles, and now this solute being insoluble, when it undergoes filtration, it gets filtered out. So all these particles that have been adsorbed will be filtered out, and the remaining solution having the only leftover sample will be collected here. Now there will be some difference, right? The difference between the quantity added, quantity added, and that remaining in the solution, gives the quantity that has been adsorbed. So the initial minus final gives the amount that has been adsorbed. So the amount that has been adsorbed indirectly gives the information about the surface area. More the surface area, more will be the adsorption rate. Now how can we interpret the results from this data? Let's see. So from this value, from this difference value, the amount adsorbed per gram of powder is calculated. So let it be x grams. We already know the number of molecules present in 1 gram mole of a material or substance is given by Avogadro's number. Now we need to interpret the data by the help of this Avogadro's number and this x grams. Now from this data we will be able to get the details of the number of molecules present in x grams, because 1 gram mole consists of this many number of molecules. Now x grams, like after conducting experiment we'll get to know x gram. The x grams of solute contains how many number of molecules? Just as cross multiplication we can get the number of molecules present in the particular x grams of solute. Like that we will be able to know the number of molecules present in the x grams. Now how can we determine the surface area? It's so simple. If we know the number of molecules present, the surface area occupied by one molecule of solute is generally known. The specific area, how can we know the specific area of the powder? By multiplying this value with the number of molecules adsorbed. So number of molecules adsorbed present in x grams into surface area occupied by one molecule of the solute. That is how we will be able to know the specific surface area. Surface area and specific surface area, how these two are differentiated is, surface area is the surface area of a particle, whereas specific surface area is the effective surface area that undergoes adsorption, that is ready to undergo some reactivity with the other molecules, other particle surface. That is known as specific surface area. So the specific surface area is calculated by multiplying this value, surface area, into the number of molecules adsorbed. Now this is actually explained by an example where the medium here we'll be making use of methanolic solution, and the solute which we use is stearic acid, insoluble one. Now we will be given some sample, say some powder sample. We need to make sure that we need to select a solute in such a way that this should be insoluble in the medium, so it would be easy for filtration. So why only stearic acid? It is a linear molecule, hence it helps, or it will promote only adsorption of monolayer. Only one layer will be adsorbed. Only one layer would be adsorbed. So we need to choose the molecule, the solute molecule, in such a way that it should be linear, because it promotes the formation of monolayer. So the molecule gets adsorbed as a monolayer. So this is the principle of using solute as adsorbate. So here now this we discussed about using a solute that forms monolayer. Now we will be discussing about using gas adsorption on powder sample. Let's see. Just like in the previous working principle, we will be having adsorbate, but here the name itself indicates we will be making use of gas as our adsorbate, whereas in the previous we have used an insoluble solid or solute, whereas here we will be considering gas as adsorbate. And the instrument which we use in this method is known as quanta sorb, because quantum and like the quantity that has been absorbed will be determined. So the instrument is known as quantisorb. The instrument which we use will be quantisorb. Now let's see how this instrument works. This is the quantisorb. This instrument has a chamber for sample and a chamber for the gas. Here in this experiment, we'll be making use of nitrogen and an inert gas, helium, we'll be making use in this experiment. Now helium, what is the purpose of using helium is it will create some inert environment here. And the adsorbate here would be our the adsorption takes place between the nitrogen gas and the sample. Now let's see just this one. Suppose if this is the plug of powder. Okay, this has powder particles that are closely arranged. Now if we pass gas through this plug, some of the gas molecules get adsorbed onto these particles and the leftover gas will be exited, right? Now here, by checking the amount of gas that has been sent, the amount of gas that has been exited, by the difference in these two quantities, we can know how much amount of gas is adsorbed onto these particles. The greater the surface area, greater would be the adsorption. The same principle is applied here. The same principle is used here. Now let's see here the working principle. Let's see the powder for which we need to determine the surface area is taken into this cell sample holder, and nitrogen in the nitrogen reservoir. Here nitrogen acts as adsorbate gas and the helium is taken in the helium reservoir, which is an inert gas. It just creates some inert environment. Now through this valve, nitrogen is sent into the sample holder. We are having so many valves through, and again in this instrument we are able to see manometers. The manometer is an instrument that detects the change in the pressure of a gas. So the initial pressure of the nitrogen is noted in this reservoir. Now how much amount of gas is present and its pressure exerted by that amount of gas is noted. Okay, and then the gas is sent through the sample and the exited gas from this exited gas, we will be able to determine the surface area. Let's see how. Now as the gas gets exited, there will be some change in the gas volume here in this reservoir, right? So as the gas moves out, there will be some change in the volume. Volume decreases. Similarly, there will be a relative change in its pressure. That relative change in the pressure will be read from the manometer. And that's how we will be able to know amount of gas absorbed onto the particle surface. Now let's see how can the results be interpreted. A thermal conductivity detector measures the amount of nitrogen absorbed at equilibrium pressure. Now this is entirely automated. So the pressure differences can be read from the manometer, and few sophisticated equipments will be having some detectors, because there will be change in the temperature because of change in its properties, the gaseous properties. Suppose if in case an equilibrium pressure is maintained across this equipment, equilibrium pressure is maintained across this equipment by maintaining some vacuum, then how can we determine the amount of gas that is absorbed? It is by means of thermal conductivity detector at equilibrium pressure. If equilibrium pressure is not maintained, a pressure difference can be created here, and that can be easily read by manometer. And simultaneously, if there is a change in this conductivity or pressures, now this is actually connected to a monitor where we can get directly the results. We will be getting some signals in the monitor which is connected to this instrument. Now this signal height actually plays a major role. See, the signal height gives the rate of absorption of the nitrogen gas. Okay, now let's see. When this instrument is connected to a monitor, say this is a monitor, now this is connected to a monitor. Now from this monitor we'll be able to see some signals. How can we interpret the signals? The signal height represents the amount of the absorption rate of nitrogen gas, and we need to know how much amount of gas that has been absorbed. This peak represents the rate of absorption, and the area under this, the area under this peak represents the amount of gas absorbed on the powder sample. This is actually a sophisticated technique where we will be getting accurate results. The rate of absorption can be read from the peak, and the amount of gas absorbed can be obtained from the area under the curve or under the peak. Now we need to know about one equation known as BET equation. Now how this amount of gas absorbed will help us to know the volume of or the surface area of the particle. It is by BET equation. BET equation is given as P by V into P naught minus P is equals to 1 by VMB. B is the constant. Okay, B is a constant. P minus 1 into P by VMB into P naught. Let's see each individual. That is a very important equation from which we can derive the surface area of a particle. Whereas V is, here V represents the volume of gas absorbed per gram of powder under pressure P. Whereas P naught is the vapor pressure of liquefied nitrogen. Vapor pressure of liquefied nitrogen. And the pressure P is the pressure that is maintained. B is a constant that is related to a gas. Here we are using nitrogen gas. It is a constant, nitrogen gas. which represents the heat of adsorption minus heat of liquefaction of nitrogen gas. This is actually a constant, will be constant for specific gases. Now, how can we interpret this data? By plotting a graph. So we will be taking from this equation, let's see, from this BET equation. So this B is constant, we'll be not considering this one. And here this is also constant, B is constant. So for a graphical plot, we will be considering this variable and this one. So we need to plot a graph by taking P by V into P naught minus P against P minus P naught. It gives a straight line. Gives a straight line. P by V into P naught minus P by P naught will get a straight line. And we need to determine its slope. Its slope would be B. Its intercept would be Vm. So from this data, we can calculate specific area. So we will be taking this intercept value into consideration to determine the specific surface area of powder sample. Now specific surface area SW is equals to AM into N by M by rho into Vm. So this is a formula used to determine the specific surface area of the powder sample. SW is equals to AM. AM is the area of the close packed gas molecule. No, this is the powder sample in the chamber and the gas when it is sent. Now AM is the area of the packed gas molecules that has been absorbed as a layer onto the powder particles. Now this is also specific for specific gases. Now for nitrogen, it would be 16.2 into 10 power minus 16 centimeter square, the area. And N is the Avogadro's number, constant. So Vm is the value which we get from the intercept, and M by rho, molar volume of the gas that has been absorbed. And now this value we will be getting from the volume that has been absorbed onto the powder particles. So here this we'll get from the graphs, this value Vm. M by rho we will be getting from the experiment itself, amount of gas absorbed. Okay, as molar volume of the gas, this one, and Am is also a constant, Avogadro's number constant. It is the Vm that helps us to calculate the specific surface area of the powder. So this is how we will be making use of gas adsorption onto the powder sample as a principle to determine the surface area. So this is about the adsorption method. So in this adsorption method, we have used solute and also gas as adsorbates. Now Another method by which we can determine particle surface area is air permeability method. Air permeability method. The name itself indicates we will be checking for the permeability of air. Here, let's see how this works. The basic principle. Now, suppose this is a tube. Now, if we let air to travel inside the tube, it can freely travel. This is case A. Now, let's consider another case B. Take a pipe and put some powder plug inside this tube and let the air flow. Do you think the air will flow freely just as in the case of A? No, because there is some obstruction in this pipe, and this powder particles or the powder plug will cause some resistance to the flow, right? So this resistance caused by this powder will be proportional to the surface area. Greater the resistance, greater will be the surface area. Very fine. Suppose if this is the plug, and then these are the particles, large particles, and this is the plug having very small particles, that are closely arranged. Now, what do you think? Let this be a case C and case D. In case C, we are having large particles in the plug, and case D, we are having small particles as a plug. Now, which case a higher resistance to airflow is seen? It is in case D. Why? Because because of smaller size, these are closely arranged as a pack. And because of larger particles, there are air spaces through which the air can be flown. So, lesser the particle size, greater is the resistance. And greater the resistance, lesser the particle size, greater will be the surface area. So that is how the resistance towards the gas can be determined to obtain the surface area of the particle. Now, this is the basic working principle in this air permeability method. Now, for this method, we'll be making use of an instrument called Fisher subsize sizer. Fisher sub-sieve sizer. Let's get into this. Now, this is the Fisher sub-sieve sizer. This is the instrument which has a chamber. In this chamber, we will be having our powder sample. This is the sample holder. And to one end of this sample holder, we will be having an inlet for gas or air to pass through it. Now, the gas or the air is passed through this at constant pressure, pressure regulator. Now, this gas is sent, and this is the dryer in such a way that the entire setup should not have any moisture, because it might affect the absorption of the gas onto the particle surface. Now the gas travels through this plug, and slowly the gas will be sent out, and here at the one end we will be having a manometer through by which we can determine the pressure differences. Suppose, let's see how this actually works. When a gas is sent, it travels through the sample holder, and then like this it will travel and then it gets exited, right? Now during this travel, some of the gaseous molecules get absorbed, and these particles present in this plug, they form as small channels. Through these channels the gas will be flown out, and the resistance to this airflow can be easily observed from the readings of manometer. Here the pressure difference would be different, and here the pressure difference would be different because of the small channels. Now let's see this part. This is our sample holder. In this sample holder we have added the powder sample, to which we need to know the specific surface area. Now if there is no sample, directly the gas will be passing through this holder freely. Now we have packed this holder with the sample, to which we need to determine surface area. Now when the gas is passed through this sample, now the spaces between the particles will act like channels for the air flow or the gas flow. So these pathways, they just act like capillaries. Through these capillaries that are between the particles, the air or the gas will be flown out. Air or the gas will be flown out. So this is the working principle. So now let's see how this works. A plug of powder is considered as capillaries. Now this plug of powder here, the pathways, these are considered as capillaries. Now this surface of the capillary represents the surface area, is the function of the surface area. Now here we need to consider Poiseuille's equation. The flow of a fluid, be it liquid or a gas, flow of a fluid through a capillary, it is actually demonstrated or better explained by considering Poiseuille's equation. V, volume of air traveling through the capillary of internal diameter d, and length of the column, and the length L, and the length L, under the pressure difference of delta P, and eta is the viscosity of the gas or the air. And when the air is allowed to pass through this plug of compacted powder, some resistance will be seen because of the compaction, because of the obstruction created by the powder particle. Now from this resistance we need to calculate our surface area. Now for this conversion we need to consider one equation known as Cosenzi-Kármán equation. which is derived from Poiseuille's equation. When we look onto this equation, we are considering one parameter, epsilon. This epsilon represents porosity, which is one of the factors or one of the properties of derived properties of powder or the particles. Now we need to consider porosity property, because here we have considered the spaces between the particles and spaces inside the particles also. All these act like as a capillary through which the air passes. So we need to consider the porosity parameter. That's why we have, we need to consider Cosensi-Karman equation. Why? Because we need to even include the porosity parameter. So we have considered this equation. This equation is derived from Poiseuille equation. V, amount of gas absorbed, is equals to A, cross-sectional area of the plug. Cross-sectional area of the plug. Here the powder plug is seen. The cross-sectional area of the plug. Eta is the viscosity of air or the gas. SW is the parameter we need to determine. SW square into delta P, pressure difference. T, temperature. K, it is a constant. For the instrumental constant, usually 5 plus or minus 0.5. L is the length, the length of the column, where A is the cross-sectional area. So we need to consider the column also, L and A. And epsilon represents the porosity of the sample. We need to know the porosity and then incorporate that value in this equation. The volume of gas absorbed can be easily read from the changes in the pressure differences that can easily be read from the manometer. So by cross multiplying this, so by taking SW square on the left side and the V on to the right hand side, we can easily determine the specific surface area of the powder. This is how we need to interpret the results from the instrument called Fisher sub-sieve sizer. Sub-sieve sizer. So it is the length of this column, cross-sectional area of this column, the porosity of the powder sample, the volume absorbed plays a major role in determining the surface area by means of Cosensi-Karman equation. So this is how we can determine the surface area of the given powder sample by considering air permeability method. Air permeability method, here the instrument used is Fisher sub-sieve sizer. This is the instrument. So we being a pharmacist, we need to know what are the different methods that can be used to determine the specific surface area of the powder sample, the particle volume of the sample given, and based on the type of instrument which we use, we need to prepare our sample. For example, for Coulter counter instrument, we cannot use dry powder sample, right? We need to mix it with electrolyte and then we need to take that as a sample. Whereas in this air permeability method, we will be not using any electrolytes directly. The powder as a plug we will be putting inside the sample holder. So that is how we, being a pharmacist, we need to know how to prepare our sample for the determination of particular properties and its measurement. This is about particle volume measurement and particle surface area measurement. So if you're having any doubts regarding this lecture, you can contact me through my mail. This lecture is in continuation with the previous lecture. Go through this lecture, and if you find difficulty, you can reach me through my mail. Thank you.